All right, let's continue on with lecture 10 here. I don't think I'm going to need the document camera for anything here, so we're just going to record this. You get to see me today. Doesn't normally happen, but here we are. If we start chapter 5 at this point, all right, starting chapter 5, what is chapter 5? If chapter 4 is first law for closed systems, then chapter 5 is first law for control volumes. And again, control volumes are systems for our purposes. Control volumes are systems where mass can cross the boundary. Mass can come into and or out of the system. So whenever I'm dealing with mass flow, I've got to keep track of that mass because mass has to be conserved. I can't create nor destroy mass. All I can do with mass is change, or it can come in, it can go out, but it can't be created nor destroyed. The only exception to that, of course, would be fusion or fission reactions. Our good friend um, uh, Albert Einstein, it's a bit of an oversimplification here, but it's correct to say that Einstein essentially came up with the understanding that energy, if I have a fusion or fission reaction, that if I basically destroy mass or convert mass into energy, it's converted along these lines where that's the amount of mass times the speed of light squared is the amount of energy that is released during a fusion or fission reaction when mass gets essentially destroyed, if you will, or converted into energy. So if I have a large uranium atom, for example, or plutonium atom, and I launch something into it to basically blow it up to get it to fizz to be destroyed, and now I've got two smaller atoms. Part of the mass does not survive that process and gets released as energy. Now the good news is we don't have to worry about this in this class. It's way beyond our discussion here, right? Mm, leave that for another class. Those of you going into nuclear engineering, kudos. That's good luck and kudos to you, right? We definitely need people to do that work, but that's beyond what we're doing here. Okay. Now, we've discussed the idea of a mass flow rate before. We've said that if I've got some sort of maybe a pipe or a conduit here, right, and we've got material flowing out of that, maybe some sort of a liquid, for example, right? Now, that stuff's going to come out at a specific speed, right? A specific speed. And I've got a cross-sectional area of that conduit. If I know the cross-sectional area of this conduit and I know the speed at which it's coming out, then I can find the mass flow rate, m dot, is going to be the density of the flow, that's mass per unit volume, times v dot, the volumetric flow, that's volume per unit time. So just on a basis of units or dimensions here, dimensional analysis, that's the words I'm looking for. Mass per volume times volume per time gives me mass per time. And how do we find this volumetric flow rate? Well, a simple way to do that is if I know the cross-sectional area of the conduit through which fluid is flowing, multiply by the speed at which that fluid is flowing, that product gives me the mass flow rate, mass per unit time. And because specific volume is the reciprocal of density, I can also write these forms of this expression, and those are all true. Right? So important that you know which V you're using. We use V to represent different things. Make sure you know which V you're dealing with because they all show up in this one formula, for example. Okay. Now, control volumes are not closed systems, as we know. So we mentioned this right up front. If I've got a control volume, that means I've got mass coming into maybe multiple places and most likely a mass also going out. Okay. Now, if what we find is that the conservation of mass for a control volume like this is going to look like this. I'm going to take the sum of all the mass flow rates across all of the inlets coming into my control volume minus the sum across all of the outlets. Everywhere mass is flowing out, I'm going to add up the rate at which all of that mass is going out. And that's going to equal the change in the mass for my system with respect to time. And this might look familiar. Well, yeah, this is a conservation law. All conservation laws take the form of in minus out equals change. In minus out equals change. It's conservation law, just like conservation of energy. If I add up the rate at which everything comes in, subtract the rate at which everything goes out, that equals the rate of change for my system. Now, most devices we will encounter are going to experience an equilibrium eventually. They're going to go through some sort of a warm-up period or a cool down period. I always like to point to a garden hose on a hot day. If I go out and I turn on water at the hydrant and I run to the end of the garden hose and I pick it up, is there water coming out immediately? Well, no, it's you got to fill up. There's a period of time, right? There's a period of time where you have mass going into that garden hose faster than what's coming out. So you have a change in the mass of that system. So you have a period of time where the garden hose is filling up. The mass of that garden hose is changing over time for a short period of time. Now, eventually, if I leave that garden hose turned on, eventually I'm going to reach an equilibrium where I have as much mass coming in, as I have going out. I reach an equilibrium. Same thing with that garden hose. If we think about that garden hose, if, let's say it's a really hot day and it's sitting out in the sun, and I walk out there, I turn on the water, and I go to the other end, and I feel the water coming out. The first water that comes out, that is hot. In fact, on a really hot day, you can burn your hand if you're not careful, especially if it's like a black hose, a really dark colored hose. It's gotten really hot. The water coming out is going to be really hot. But over a long enough period of time, the garden hose itself is going to cool down. So if the garden hose is the system, over a period of time, the system can lose energy. The dE system dt is non-zero. However, once we reach an equilibrium, over a long enough period of time, we'll reach a point where if I can maintain the same inlet and outlet conditions, eventually we'll reach this steady flow or equilibrium, or sometimes referred to as steady state. We can reach this point where nothing's actually changing over time. Nothing's changing over a period of time. That's the kind of problems we're going to deal with quite a bit, because partly because we haven't had differential. I'm not assuming you've had differential equations yet. So, if we look at the conservation of mass, for example, and we just drew this up earlier, we say if I add up across all of the inlets, the rate at which mass is coming into the system, and I subtract all of the mass flow going out, that's going to equal the change in the mass for my system with respect to time. Now, again, if I have steady flow, we just mentioned that earlier. If I have steady flow, that means I've reached this equilibrium point. I've reached a point where there's no change in my system with respect to time. If it's steady flow, that means this differential term goes to zero. And now I've got a scenario where if I add up everywhere mass is coming in, that's going to equal the sum across everywhere mass is going out. The rate of mass in is going to equal the rate of mass out. Okay. And if I make the same steady flow assumption for energy, remember the first law says, in its purest, rawest differential equation form, says the rate of energy in minus the rate of energy out is equal to the change in the energy of the system, dE system, with respect to time, dE dt. Well, if it's steady flow, this term goes to zero. And you can write E dot in is equal to E dot out. How I normally leave it, I normally write it as E dot in minus E dot out is equal to zero. And I normally leave it like that. And we'll see why as we progress through the course. But if I've got a steady flow scenario, in some textbooks, they'll call it steady state. It's a very common term. If you talk to engineers my age or older, we probably learned it as steady state. Steady flow is another way of saying the same thing. Your physicists and your scientists might call it equilibrium, and we're basically saying the same thing. We're saying a situation where nothing's changing over time. It stabilizes over time so that all the DDTs go to zero. And now I don't have differential equations. Now the conservation of mass is no longer a differential equation. Now the conservation of energy, no longer a differential equation. I don't need to understand differential equations to solve this. I just need to know the rate at which energy comes in minus the rate at which energy goes out. That sum is zero. So the last thing to mention here, I think we can get this done in this video. Yeah, I got time. We'll do this in this video and we'll probably call this done, is the work done by flowing fluid. So if I have some sort of a pipe, for example, or conduit, right? And let's say that I've got flow going, okay? So if I wanted to look at the energy, E dot, of mass, let's say coming in, the rate at which energy is carried in by mass. Well, here's what I know, that what energy does that mass that's coming in have? Well, it's got its own internal energy, and it's got its own kinetic energy, its own potential energy, just like any other system. I basically have kind of a little bubble of mass in here, so kind of its own little system. And it's moving at a particular rate. So the mass is flowing at a particular rate, and that mass has its own internal energy. It has its own kinetic energy, v squared over 2, and it has its own potential energy. Very high-tech demonstration device here, right? So I'll normally have this out in class. I've just got clear tube here with some water in it, and I'll say, yeah, I'll hold this up to the class and I'll say, is the water in here flowing, right? Is this water flowing right now? It's not a trick question, right? Is the water flowing? No, it's not flowing. And as long as I hold it good and still, it's not flowing at all. And I'll say, okay, well, how do we make it flow? How can we make it flow? And somebody will say, well, you tilt it, right? And you can see if I tilt it, right, you can see the water getting right there to the edge. I'm not going to put it, I don't want to pour out on my surface here, so I'm not going to make it flow. But yeah, you can see what I'm doing there. I can make it flow eventually. Eventually it's going to come out this end if I raise that up enough, right? Okay. Somebody might say, well, you can blow on it, right? Right? You can see I'm not, I don't want to squirt this tablet. It's not, I'm actually borrowing it. So I don't want to get water on it. But you can see what I'm saying, right? It's just sitting here, right? If the water is just sitting here in the tube right now, all it has is internal energy, kinetic energy, and potential energy. That's all it has. It's not actually flowing. Something has to make it flow. What makes it flow? Well, I can either use gravity to generate pressure, I can blow on it and push it out with pressure. What we find is in an enclosed system, your textbook likes to say, well, your textbook likes to say, pretend that the fluid upstream is acting like a piston, pushing that fluid downstream. And it's doing that by pressure. Now, pressure itself is not energy. Notice these are all energy per unit mass. Pressure is not energy, and it's not energy per unit mass. I need to use something to make it energy. And what I can do is multiply it by the specific volume of the fluid, which basically represents the specific volume of this block of fluid, this bubble of fluid, this that we've isolated within this system. And we say, well, basically for this fluid to flow, you have to do a little bit of work to it. That work is done by the pressure of the fluid upstream, basically acting like a piston, pushing the volume of fluid downstream. And that's what this term is. Now notice, and you're more than welcome to add U plus PV every time you need to do a calculation here. But notice we don't have to. That's already done for us. U plus PV by definition is H. So if I'm dealing with the energy of mass flowing in or out of a system, I'm going to use the H value because it represents the energy of that mass plus the push upstream to make it go downstream. So I'm going to finish this video out here. I'm going to introduce to you the concept, the first law of thermodynamics for steady flow control volume. Right? I don't think I've got, what do we got? Anything. No, okay. I want to make sure I didn't have control volume behind me there. E dot, not equals, E dot in minus E dot out is equal to dE system dt. And if it's steady flow, this goes to 0. Now, we need to think about all of the energies that can cross the boundary for a control volume. Well, that's going to be heat. So it's Q dot in plus W dot in, the rate at which work can be done, or the power input. Again, power is specifically referring to work rate. So the rate at which work is done, or the power input, plus E dot mass in, the rate at which mass comes into the system. And then minus all these things going out, minus Q dot out, minus the power output, W dot out, minus E dot mass out, the rate at which mass carries energy out of the system. And this simplifies, well, it doesn't simplify. We can expand this, right? We just talked about the energy of this flowing fluid is going to be m dot h v squared plus gz. Now, what we want to do here is, well, let's just do this. Let's say Q dot in plus the power input plus, let's talk about all of the energy that can come into the system. So I'm going to do a summation across all of the inlets, the rate at which the mass is flowing times h plus v squared over 2 plus gz. And then I need to subtract all these going out. Subtract the rate at which heat goes out. Subtract the power output, the rate at which work is being extracted, W dot out. Minus, I should be saying minus here, minus Q dot out, minus the power output, minus the summation across all of the outlets, the rate at which mass is flowing out, m dot, times quantity, the enthalpy, H, plus V squared over 2 plus GZ. So the sum of all of the energies that is going out with the mass, and that whole sum is equal to 0. This is still in minus out equals change. I've added all the energies coming in, subtracted all the energies going out, and that is still equal to the change. And it just so happens the change is 0. Right? Now, I'm going to finish there. That's a nice stopping place, and that's a little longer than my normal 15 minutes, and that gets us a good lecture 10. That's where we'll be. We'll see you guys next time.